Hey, I'm dripping sweat. Yo, what's up? Yo, 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 yo. That's right. Okay. Okay, live stream. Okay. Okay. Live exam 2 review. To review now. All right, here we go. Save that. One more second. You guys see that? Oh, okay. You can't see that. Okay. It's the wrong computer. Of course. Is this just hot and sweaty, or is it me? Okay, it's just me? Okay. Ooh, man, I'm going to get a workout here. All right, here we go. Okay, post that. And then test it. Oh, yeah, test it over here. Okay, I think I'm live. I think it's working. Okay, it says it's good. Okay, hi, everybody. How you guys doing? So if you're ready, actually, here, I want to ask you guys, let's take a quick vote. We have 4 chapters. 5, 6, 7, 8. Do you want to start backwards, start with 8? Raise your hand, I want to start with 8. Raise your hand, I want to start with 5. Okay, so actually it looks like the 5's won, but we'll go through it, right? It's going to go through the whole thing. I just want to quickly test that it's working, if you don't mind. So you're going to see, I'm going to do the repeat thing, right? Let's see. Testing. Can you hear me at home? For all our home viewers. Yes, okay, all right. Let's see, announcements. Exam 2 review, okay. Hello. It looks like it might be. Okay, I gotta stop. Alrighty, so let's talk about astronomy, exam 2. Okay, so here are the chapter 5 terms right here. So I think we can go through a lot of these terms pretty quickly, but if you want me to stop, make sure you stop and ask for a little bit of extra. Jill, I got your sleeping bag and your stuff, right? Do you want it now? Can I give it to you now? So you don't forget, because you're gonna leave without it. And your dad's container. Yeah, all right. Okay, there you go. She went camping with us at the Astronomy Club. Okay, so first term, Kuiper Belt object. What's the Kuiper Belt object? An object in the Kuiper Belt. But where is the Kuiper Belt? Tell me about that. Kuiper Belt, past the orbit of Neptune, just outside of Neptune. What comes from the Kuiper Belt? Visiting the sun, leaving a trail behind it a lot of times? Comets, for example. What type of comets? Short period comets come from the Kuiper Belt. Kuiper Belt objects are very icy because there's lots and lots of icy stuff out there. What's an exoplanet? Do I need more Kuiper Belt objects? Pretty good, right? It's a disk that goes around our solar system. There's another thing around it called the scatter disk, which is a donut shape. And then finally, there's a spherical shape called the Oort cloud, but we're going to be getting that in just a second. Okay, so back to the next one, exoplanet. What's an exoplanet? A planet orbiting another star, right? And how many exoplanets do we know about now? Almost 6,000 of them. You don't have to know that necessarily, but there are a lot of them. The only one I think I mentioned in there is called TRAPPIST-1. Does anybody know why TRAPPIST-1 is kind of important? We'll come back to that in a second. Yeah, but not 7, but it has 3 habitable ones. Yeah, actually, there's a number of Earth-sized planets that are in the habitable zone, right? I think it's about 3 that are actually in the habitable zone, but they're Earth-sized as well. So they're going to have, what's habitable mean? Goldilocks zone. Liquid water can exist at the surface of the planet, right? That's pretty exciting. So it's got the right amount of gravity. It's got liquid water. Could be a pretty cool place to move to in a long time. Okay, it's going to take a long time. Okay, next one, Dwarf Planet. Who are we talking about in particular? Pluto. Pluto got demoted from a full-fledged planet to a dwarf planet. Can you tell me what a dwarf planet is? It satisfies the first 2 criteria for being a planet, but not the third one. So let's go over those. Yeah, go ahead. Okay, so the one that it doesn't do is it doesn't clear out its orbital path. But it does do what? Orbit the sun, right? Pluto orbits the sun. Number 2, it's a sphere, right? So it's sphere, meaning it has enough mass to shape itself into the shape of a sphere. But number 3, sweeping out the orbital path, it doesn't do that. So that makes it a dwarf planet. There are probably 1,000 of those in what area of the solar system? In the Kuiper Belt. That's another reason to know about the Kuiper Belt. So there's going to be a lot of objects that we're going to discover in the Kuiper. We've discovered a few of them so far. Okay, asteroid belt, another belt. Where does that found? Between Mars and Jupiter. But there's a gap. Remember, there's a gap between Jupiter and the asteroid belt, much bigger than between Mars and the asteroid, the main belt, right? That's the main belt. Why is that? Why is there a bigger gap between Jupiter and the belt and Mars and the belt? Jupiter was more massive. It really swept out its orbital path very effectively. So we have a big clearing about there. But did the asteroid belt, does it really just go from Mars to Jupiter in that area? Or did we find out something else, right? Are there some that are in the orbit of Earth area, Earth crossing asteroids? We have some inside of that area as well. Okay, Kuiper Belt, we just mentioned it. Kuiper Belt outside of, I already said this, right? Redundant, okay. Scattered disk is a donut shape. Don't know much about it, never seen anything from there, but it's a hypothetical place where we see potentially objects coming from it. It's again, coming from simulations probably. So don't know, it's just our author has put it in there. So it goes main solar system, Kuiper Belt, scattered disk, and then Oort cloud. That's our complete solar system, okay? Oort cloud, right? That's actually another important one because it's hypothetical, never seen anything. I'm sorry, we've never seen an object out there, but we've seen many objects come from there. What comes from there? A long period comet. Yeah, make sure you know. Short period comets, less than 200 years, they come from the Kuiper Belt. But the long period comets come from really, really far out, and they are, we think, coming from this place called the Oort cloud. But it's spherical, so the comets can come from any direction. So what's a long period comet? How long does it take to get in and out? It can be taking 1 million years or more, right? So more than 200 years. Close the door? No. Oh, you got, yeah, they're way out. Totally way out there. They are way out there. Okay, terrestrial planet. What do we got? Which planets are terrestrial planet in our solar system? Mars, okay, going backwards, okay. Earth, Venus, and Mercury, right? The inner ones. What do you know about what's special about those? They all have something. They're solid, they're rocky. They have cores made of iron and nickel, and they have mantles made of silicate. They all have that. They all have a crust, right? So they have core mantle crust. But Mercury, we noticed, had more, for its body size, had a much larger core. Why do we think that's true? Why do we think that Mercury has such a large core compared to its overall mass? Because it's close to the sun, that's where the metals formed first, right? They were the first crystals to come out of the gases of our solar system. As you got further away, you began to see silicates, right? This is called the condensation sequence. I'm jumping a little bit out of order. Somewhere it's in here. But we have metal oxide, silicates. A little bit further out, about 4.5 AU, we have the snow line, ice line, where water ice could crystallize. And then way out there, we have the other kinds of ices, right? Those are the 4 that I asked you to know about. Okay, a gas giant. What are the names of the planets that are gas giants in our solar system? Jupiter and Saturn, right? So what's true about them? They both have, what's the major components of both of those planets? Hydrogen and helium, just like the sun, right? This is going to be important after Tuesday's test. On Thursday, we'll start talking about stars, right? And so we'll get to our sun, which is kind of cool. And finally, we have the ice giants. What's an ice giant? What are the names? Uranus and Neptune, right? So Uranus is the one that comes before Neptune. And what's special? Why are they called the ice giants? Lots of what? Lots of ice, right? They have a lot of ice. So not as much hydrogen and helium. They do have that, but much more ice, and it's in the mantle part of their bodies, right? The mantle is where we see a circulation of icy material. Okay. So uncompressed density just refers to the density, the average density of the planet, and which planets are more dense and which planets are less dense. Which ones are more dense? The most dense ones in the solar system are found close to the sun, the terrestrial ones. They're much denser. And then when we talk about Jupiter, Saturn, Uranus, Neptune, do you remember which one is the least dense? It would float in, yeah, Saturn would float in a bathtub. I mean, it's a joke. You can't really do that, but it's the one that would float. The other ones are pretty similar. I think, what was it? Neptune was a little bit more, right? Just slightly more than Uranus and Jupiter. Okay, and planetesimal. Okay, we're going to talk about the formation of the solar system. We're going to get to this. Okay, planetesimal. What do we mean by? I'm just going to go through the vocabulary. Planetesimal. What's that? Yeah, chunk of matter, the size of a car, maybe a little bit. An asteroid size. Actually, that's a pretty good one. Asteroid size chunk of matter that would eventually be merged together to form a protoplanet, which would then be large enough to become a full-fledged planet. But a planetesimal is a chunk of matter that is pretty large, but not super large, right? So do we have any objects that big in the solar system? Well, yeah, the asteroid belt, right? And so what do you know about the asteroid belt? It's made up of different kinds of asteroids. What are the three types? Coming up to this. All right, I'm jumping. I'll talk about it later. Trojan asteroids, which ones are those? Actually, at this moment, I feel like I should probably stop and draw a figure. Do you guys remember where the Trojans are located? You do need to know that. Yeah. That's right. To the side, they're at the same orbital distance from the sun. I'm going to try this out. I've never used this whiteboard before. Whoa! Okay. I got a new whiteboard. Actually, it's not mine, but I'm using it. Okay. So where are the Trojans located? So it's kind of low. Can you guys see it? I think I'll just erase every time, right? So that you guys have a fresh board. That's kind of cool. I think I like this. Wild thing. I think I love you. All right, here we go. But I want to know for sure. Okay, here we go. So, okay, so the sun's in the middle, and this is a planet. Let me go ahead and put whatever planet. It's Jupiter, right? Okay, so if I draw a line between the sun and Jupiter, where are the Trojan asteroids found? So they're in front and behind by 60 degrees. That's crazy. It's so mathematical, right? But so 60 degrees in front of Jupiter, you find a little cluster of asteroids, and 60 degrees behind Jupiter, right? 60 degrees behind. So these are called the Trojan asteroids. And the thing is, what's important? Why do you need to know that? Actually, it's going to be coming up in a second. What's happening in these special places is the gravity from Jupiter and the gravity from the sun work together to make this a stable orbital place. So they orbit with Jupiter as Jupiter goes around. These things just get stuck there. They're kind of cool. So we also have them. Earth has them. Actually, all the planets apparently have them. Someone told me that the other day. I don't remember seeing that, but I know that Earth and Jupiter do, and it looks like maybe all of them do. And it's a mathematical place where the gravity from the sun and the planet works together, okay? All right, let's see if this goes back. There we go, cool. This is so awesome. Boy, this is so pro. You guys seeing me become more pro, right? All right, anyways, Lagrange points. Oh, after all of that, I just realized I should have stayed back. Oh man, that's not pro. I go right back to the board. Oh my God. Okay, that's funny. Okay, you guys, this is just all a joke, right? Okay. All right, here we go. So let's talk about the Lagrange points. How many Lagrange points are there? There are 5 Lagrange points. Okay, so let me do that in color, right? These happen to be a couple of them, but they're not the first ones. So let's go ahead and do them in order. So the first position is actually it sits between any two bodies. So it could be sun and planet, or what would be another good one? Between the Earth and the moon. That would be another example of 2 gravitational bodies. There are 5 special locations, right? So one of them is located between the sun and that body. It's called L1. The second one is on the far side of that body, called L2. The third one is actually on the other side of the major body. It's called L3. And then these are actually two of the Lagrange positions, L4 and L5. Okay, so it turns out the Trojans are located at a couple of Lagrange points, which is kind of cool. It was actually discovered independently way before we ever saw them. Mathematically, the guy Lagrange described these special places that they should exist. Yeah. Do they change? No, they stay with each pair of bodies, right? So they're locked in with this body that moves, so Jupiter. In the case of the Earth and the Sun, again, it would move with the Earth and the Moon, that's what I meant to say. They would move with the Moon around the orbit of the Earth. Ooh, that's smart, because I'll be working over there. That's good. She's thinking. That's awesome. All right. Okay. So Earth-crossing asteroids. We mentioned those before. What are those? Asteroids that cross the path of the Earth could one day destroy all life on Earth. Sorry about that. But it's reality, right? They have the potential of eventually hitting Earth. There are none in the near future that are going to hit Earth, but you never know, right? So we should always be prepared. By the way, live each day, because today is today and you're alive, and isn't that awesome, right? So did you already tell somebody you love them, right? If not, find somebody that you love, right? And tell them you love them. Okay, never mind. All right, differentiation. What are we talking about? Differentiation. Let's talk about the asteroids. That's what the next few words are all about. So in the asteroid belt, we did get the formation of larger bodies, not quite planet-sized bodies, but we called them protoplanetary bodies. And if they're large enough and they're hot enough, they can differentiate. What does that word mean? Differentiate. Separate, yeah. Right, and because of the different densities. Okay, so separating into layers because of the different densities. So this is how you get a core made of iron and nickel, right? And then a mantle layer made of silicates. And yeah, that's it, right? That's pretty much all you have to worry about. So some of the largest bodies in the asteroid belt formed little protoplanets. And then they smashed into each other and broke apart. And the cores became what kind of asteroid? The core material became what kind of asteroid? M-type, metal-type asteroids came from the core of a differentiated protoplanet, right? That smashed apart. And so there are families of M-type asteroids that probably once upon a time were part of a single body. And then what do you get from the mantle? What type of asteroid? You get S-type or silicate-type asteroids, stony type, right? Silicate type. And the last type, which is the most common type, is the C-type. What does C-type stand for? Carbonaceous, right? Those are the ones that have lots of organic compounds and other things. They never actually were part of a larger body. So they're made up of the raw materials that we think the solar system is made of. So they really are as old as the solar system, right? They're really special, which is why we like them when we find them. But they're very difficult to find. They don't survive usually. Okay, so S-type, M-type. Okay, I've already kind of mentioned snow line. Where's the snow line in our solar system? 4.5 AU. So which planets are inside the snow line? Like closer to the sun, that would be the terrestrial planets. And then outside is all the giants, the Jovian planets. Jupiter, Saturn, Uranus, and Neptune are all outside the snow line or ice line, which means what? They will all have ice, either in their bodies or in their moon's bodies, right? They will have ice. Okay, albedo, term we learned in this section of the course. What does albedo mean? The reflectivity, right? So high albedo means reflects light really well. Low albedo means very dark. It does not reflect light very well. We'll mention that when we talk about the moon, right? So there's lunar highlands, and we'll come back to it in a minute, okay, when we get to the moon. Comet nucleus, we're talking about comets, right? What's a nucleus of a comet? The hard stuff in the middle, right? The hard, icy bodies, right? So what's the nickname for a comet? Dirty snowball, right? Mostly made of ices, all kinds of ices, not just water ice. Remember what kinds of ices? We did it in class. CO2 ice, alcohol ice, methane ice, right? All these, ammonia ice, nitrogen ice, oxygen ice, all of these different forms that are ices, right? It's really cold. Okay, so the coma, what's the coma? The atmosphere around the nucleus is called the coma. Why does it form? When the comet is coming closer to the sun, the heat energy from the sun causes those gases to turn from a solid into a gas. What's the word? Sublimation. They sublimate and form an atmosphere. And then as the comet goes away from the sun, what happens to those gases? They get deposited back on the comet again. They stop being present, right? So comets don't always have comas. They don't always have tails. When do they have comas and tails? When they're coming close to the sun, right? When they're near the sun, closer to the sun. Okay, so there are actually two tails. The two tails are known as the ion tail and the dusty tail. The dust tail is supposed to be neutral particles, right? Neutral particles means the charge is zero, right? So the ion tail points in what direction? Directly away from the sun, whereas the dust tail actually has a little curve to it. So if I showed you a picture of a comet, right, just a generic comet on a path, right? I think I'm going to just show you. You guys are supposed to be able to identify which is which, right? So I see a comet. And by the way, we're waiting for a big comet to come by. We haven't seen one in a while. Ooh, actually, shoot. I should mention this. It's not on your test, but there's another comet, an object which looks exactly like a comet, which is coming from outside of our solar system. Anybody hear about this? So exciting. And on my birthday, December 7th, it's going to reach the closest point to the sun. I'm so stoked. I'm going to maybe it'll have a tail. We don't know. Anyway, so you see a comet. Comets are on highly elliptical paths around the sun. And so at different places on the orbit, right, you can have a comet at 3 different places. I'm going to try to talk about the tail there. So what direction would the ion tail point? I have different colors. Why don't I do it? Okay, let's do the ion tail first, right? So if you draw a line to the comet, what direction is the ion tail? Exactly away from the sun, right? So it's away from the sun because it is energized. The solar wind is made up of charged particles. So the charged particles in the tail react very strongly. So at each one of these points, the ion tail is pointing straight away. And you'll have the longest tail when you're closest to the sun, right? This is the ion tail. Okay, what about the other tail? What's the other tail? The dust tail. Well, the dust tail remembers where it was, right? Where was it just a little while ago? So it's not just this way. It's got a little curve that goes in the direction that it was just located, okay? So the curved tail is our dust tail. You guys read that? Okay. Okay. All right. Now I'm feeling pro again. Okay, here we go. Let's see. We got our tail. Short period comet, we already mentioned this. Short period less than 200 years. Give me an example of a short period comet. Halley's Comet, right? 76 years, 75.3 years. Okay. And then we have the long period comet, which are more than 200, but actually they can have millions of years. Rosetta mission. Ooh, super exciting. Rosetta mission. I love this mission. You will definitely have 1 or 2 questions on this mission. Who was it that sent the mission? Anybody know? Was it NASA? It was not NASA, although we collaborated, right? I say we, NASA collaborated with them. It was the European Space Administration, ESA. Okay, so it was the Europeans this time. We did some awesome science. And the name of the comet is right there, Churyumov-Gerasimenko, right? You have to know that. You have to memorize that. Just kidding. No, you don't have to. But you should try to recognize it if you can. Churyumov-Gerasimenko, or 67P is the short name, okay? So we went to visit this comet, and we got the best pictures of comets that we have ever seen. And, you know, again, we could go on and on and on, but we discovered, for example, does the water on comets, is it the same as the water on Earth? No, not this one at least. So this is a question that people have been asking for a long time. We finally got the answer to that. But we did find molecular oxygen, but nobody had seen that before. So first time we actually saw oxygen coming out of the comet. All kinds of organic compounds, right? Really interesting chain molecules. We saw the magnetodynamics of a comet. Anyways, lots and lots of stuff. Pretty exciting. And it dropped a little lander down to the surface. Unfortunately, there were some errors, some problems, and it failed, right? But it lasted long enough to be able to send radio transmissions through the comet, and they discovered one really key part that you need to know. Comets are mostly empty space, like almost 85% empty space, which is actually something that I hope you kind of get an idea of. It's because the materials, the icy materials inside of it, are sublimating year after year after year, and leaving pockets behind. So it's mostly empty inside, right? Very porous, like a sponge almost. So eventually, when all the ices are gone, what will you be left with? It's called a burnt out comet. What's another nickname? Okay, so we said a dirty snowball, but it becomes an icy dirt ball, right? There won't be much ice left, and it won't have a tail anymore because there's no ice, right? Okay. Okay, boom, we're done. Okay, that was it. Just a couple of cool things, right? But it was a mission that was very successful. Learned a whole lot about Comet. What was that? Shoot 'em up. That's was it? I would guess so. Yeah, I would definitely guess so. Shoot 'em up. Anybody Russian? Absolutely. It sounds Russian. I don't know, but I'm pretty sure it is. Yeah, I don't think you need to know that, though. You could go look that up, though. Tell us. That would probably be named after the people who found it first, right? Okay, a meteoroid, meteor, meteorite, bolide. These are words that describe objects. Meteoroid, what is that one? And you need to know this, right? It's outside of the Earth atmosphere, has not fallen in, but it has the potential to fall in. So we call it a meteoroid, right? Something that could one day hit the Earth. A meteor is in the act of falling, right? It's flying through the atmosphere. What do we see? We see a streak of light, right? That streak of light is a meteor flying through the sky, the shooting stars, right? So shooting stars are pretty tiny. One of the things, there's a question will come up, you have to know the answer. How big is a typical meteor? The size of a grain of sand. How can it make this big streak of light? Well, it's not a big streak of light. It's a little tiny one, by the way, most of the time. But it has a lot of what kind of energy, even though it's just a grain of sand? What kind? It does, but where did that thermal energy come from? It came from kinetic energy, right? So the really fast little particles, even though they're small, still carry a lot of kinetic energy, and they can light up a little path in the sky. Meteorite is something that you pick up off the ground, and a bolide, I'm not sure if you're going to have a question, but you should know, it's a meteor that explodes, right? So I did show you a quick video of the, what was it called? Chelyabinsk, sorry. The one that exploded over Chelyabinsk, Russia, and then there was a flash, and the windows blew open, right? That was actually a bolide, an exploding meteor, and then the fragments would rain down on the ground. If you pick it up off the ground, though, that's a meteorite, okay? So again, I don't see it up here, but you're actually supposed to know the names of the meteorites. Do you know the names? Actually, I'm going to mention them to you guys right now. What are they called? There's iron meteorites, right? They are made of iron and nickel, right? So they are kind of correlated with the M-type asteroids, right? They would probably came from an M-type asteroid. And then we have the stony meteorites, which are made of rocky material. In fact, they're really difficult to tell. And I did find one. I found this beautiful, I didn't find one, sorry. I found one in a drawer as I was cleaning. And I'm like, why didn't I have this earlier? Because I could have passed it around and showed my students, but I have it now. So it is pretty cool looking, but it looks like a rock on the outside. You can't even tell. And then we have the stony iron, which probably came from the interface between the core and the mantle, right? They have a little bit of metal, a little bit of stony stuff. And then we have the carbonaceous chondrite or carbonaceous, which came from a C-type asteroid, okay? A meteor shower, very different than a meteor, a single meteor. Meteor shower is a whole bunch of things that happen. Sometimes, one a minute, sometimes multiple per minute, although I haven't seen too many of those. Why do we get a meteor shower? Because The Earth is passing through the debris left behind by a comet. So every new comet leaves behind a trail of debris, and when we pass through that at the same time of the year, we have a meteor shower. So they are predictable. So meteors are not normally predictable, but we know we're going to get a lot when we have the same period of time of the year when we pass through that orbit of the comet. Okay, interstellar gas. We're talking about interstellar gas between the stars, right? The gas between the stars. So when you make a solar system, you have a bunch of stuff, right? A big cloud of gas and dust. We're going to talk more about this actually on Thursday. But what happens is something starts it, a little seed is created, and this big gas cloud begins to collapse, right? Now, it must have had a little tiny swirl to it. We know that because what happens when you compress it down to a much smaller size? What has to happen? It has to rotate faster, right? And we know the name for this. You guys need to know the name of this principle. Conservation of angular momentum, right? That is a single principle that describes how something that's rotating, when you compress it down to a smaller size, has to rotate faster. It must rotate faster. And then what happens as a result of that? It flattens into the shape of a pancake, into a disc shape. Okay, so the whole solar system formed from the same original dust cloud, right? That's important. So all the planets go the same direction around the sun, right? That's just part of the original structure. And we did see pictures. Oh, it's coming up here. The protoplanetaries. You saw pictures of brand new baby solar systems where there's little rings of missing material. What's going on? A planet is forming there, right? And it's sweeping up its orbital path. Okay. Center of mass, pretty important concept. Actually, I'm going to go back to the board. There are two kinds of center of mass we went over. Actually, two kinds of problems. Center of mass is one idea. It says that when you have two or more objects, you can talk about the center of mass of the collection or the system, right? So the center of mass that you need to know about is two identically shaped objects or identical mass objects, and two that are different masses. Okay, you need both of those ideas. So just to quickly highlight those, there is a question at least on this, maybe more, but it's a key idea. You got to get this idea. So let's say we have a pair of binary stars, right? A pair of binary stars. They have the same mass, right? They're both pretty large masses, right? And where is the center of mass of the single star? Of a single star? And the answer is right at the center of it, right? Where's the center of mass? Well, so that each one has a center of mass where they are located, right? What about the system, the pair? What's the center of mass of the pair? And so you have to draw a line between them. And where is the center of mass? Mathematically, it's right in the middle. Okay, so the key idea here is that how do the stars orbit each other? And the answer is they orbit a common center of mass. And so if you take the distance between the center of mass and that body, you know the orbital radius. And because they're the same mass, what would you expect? They would be the same radius. And so actually, I'll draw a circle. I didn't draw a very good circle, but you just pretend I drew a perfect circle, right? And therefore, the stars are going to orbit. And what does that mean? If one star is going up, what does the other star have to be doing? It has to be going down. Okay? Otherwise, they wouldn't stay across from each other on the circle. So this has to happen. It has to be exactly like this. Now, those of us on Earth might actually be looking at the stars, and we would notice something about the light from the stars. What do we notice? It is changed, right? What's the word for that? If the light of a star is, if a star is approaching us, we see the frequency, the color shifted which way? Towards a higher frequency. What's the name for it? A blue shift, right? You need to remember that's called a blue shift. So the light of the star is not going to be the original light. It'll be a little bit higher energy, higher frequency. And on the other side, the other star will have it's going away from us, is going to have a red shift. What about the size of the shift? Will it be the same or different? The size of the shift, meaning the amount of change in the color. It would be the same because the speeds are the same. Okay? So one will have a red, and one will have a red, one will have a blue. Okay, everybody clear? Okay. Now, the more interesting story this is kind of interesting, but kind of easy to understand, is what if you have a star and you have a planet, right? Let's say you have a planet, which is a much smaller mass, right? The planet mass is little m, the star's mass is big M. What happens now? Oh, is this backwards? Uh-oh. Oh, well. Can you guys read this? All right, I don't know. If it should be okay, right? I got it. I don't know. Other reason, they probably can figure it out. They figured out from the words, right? Okay, where is the center of mass? Towards the larger mass, right? So, and actually, remember that stars are like 100 times. Sorry, what, is that right? 100 times? No, actually, like, anybody know how much bigger stars are? Like 1,000,000 times as massive as planets, right? Millions of times. Jupiter's like 1/1000th, but basically Jupiter's a pretty big planet. So where is the center of mass? Actually, it turns out it's going to be really close to the big one, maybe even inside of the star. But let's go ahead and just put it like just outside the star. How about that? Okay, just outside the star, you're going to have the center of mass. So what happens to the star? How big of an orbit does it have? It has a little tiny orbit, right? A little tiny circle. And the big and the planet has to do a big orbit. Okay, so this is an important idea. It means that in this partnership, which one is going to have to move faster and which one has to move slower? The planet, the small mass, is going to have to move really fast. It has to get all the way around this circle in the same amount of time. They do have the same periods, right? And so this one has a little tiny velocity. And again, if we're watching from below here, right? If we're on Earth looking up, what do we see? And again, pretend that this is a star because it's not. But anyways, pretend. What do you see for the shift? Blue shift or red shift for the star? It's a blue shift, but very tiny blue shift, right? And then on if the planet was emitting light, what kind of shift? A red shift, then it would be a very large red shift. Okay, it doesn't quite work because planets don't radiate their own light, but it's the idea, okay? Questions? Yeah. But eventually it would be reversed, right? Very good, yes. Eventually, when the star is over here and the planet's over here, yes, the planet will be the one coming towards us and have a really large blue shift, and then the star would have a red shift, exactly right. So what happens to the star? It is wobbling because of the influence of the planet that's next to it, okay? And that wobble is something that we can detect, okay? So we're going to talk about that in just a moment, right? It's one of the methods for finding an exoplanet. One of the 3 methods, okay? In fact, why don't we talk about it? Because that's the one right now. It's the one where you measure the Doppler effect. It's known as the radial velocity method, because the star has to be coming towards you or away from you on a radius, right? A radius meaning a distance from us, right? So when the star comes towards us, we see a blue shift, away from us, a red shift. That's the radial velocity method. And so I talked about the fact that there's 3 techniques. Do you remember which one was most effective, kind of effective, not so effective? This one is kind of effective, right? Actually, it's pretty good, especially if you know a planet is there, then you can watch more carefully or try to watch more carefully. So it's actually a pretty powerful technique. So I would call it technique number 2 in terms of power, right? How effective? Radial velocity, number 2, effective, right? What about the number 1 effective method? The one that is so amazing because you know, this is just transformed. Since I've been teaching this class, we went from knowing about 20 exoplanets to know 6,000. Okay, you guys understand this? It's like, this is crazy what's happened. It's so exciting. So there was a mission, and I'm getting shivers on the back of my neck just thinking about how amazing this is, right? The Kepler Space Telescope. You need to know the name. Kepler was the name of the telescope, and it watched stars, like 1,500 stars simultaneously. And as it watched them, it monitored the light level coming from the star. It's called the light curve. And what happens if an exoplanet passes right in front of the star? It dims just a little tiny bit. And this is called the transit method. So how effective is the transit method? Super, super effective. The most amazing method that we've ever come up with, right? This is the one that's generated like 5,000 planets, right? 5,000 possible planets. And there is one more method. I seem to have left it off. It's not so effective, but it is maybe getting better. Anybody know the third method for detecting an exoplanet? Direct imaging, taking a photograph, direct imaging. Very, very ineffective, very difficult to do. But you guys saw the picture, I think, on the you saw the picture on Wikipedia of direct detection, and that shows that it has. I shouldn't waste your time. This is that, but it's so cool because it has potential, right? Exoplanet. It has potential. Okay, I'm getting off target. All right, here we go. Direct detection, direct imaging, radial velocity, direct imaging. Okay. Okay, well, that's not the one. Oh, that's pretty good. Okay, it's called. All right. Where's that cool one? All right, I'm getting off topic. You don't need to know. Okay, it's not that important. But there was one where you could see 4 at the same time. All right, anyways, whatever. No big deal. Okay, super Earth. What's a super Earth? A Earth-sized object, but maybe up to 2 times the mass of the Earth. So it's the Earth-sized, a little bit bigger maybe. And so we think that we could live on a planet like that, basically. That's kind of one of the criteria. So you and I, we would not do really well in extreme gravitational environments. So I want you to imagine that you had to carry around your amount of weight in a backpack. How happy would you be? Right? That's a lot of weight. But that's what we would experience if we lived on a planet with 2 Gs of gravitational acceleration. So a larger planet would have more gravitational field. It could be, it could be done. We'd probably get stronger, right? You train after a while and you grow up in that and you become stronger. So human beings that grew, lived in that environment over time would probably get stronger. But anyways, this is kind of like the limit of what we could imagine doing. Okay, habitable zone. We mentioned already the Goldilocks zone is the place near a star where you can have liquid water at the surface, okay? A hot Jupiter, what's that? A massive planet next to a star, big massive planet next to a star. So actually, I want to tell you that the radial velocity method first discovered hot Jupiters, right? Why did they do that? So number 1, why did they find hot Jupiters? A Jupiter-sized planet causes a big wobble or a small wobble on a star. A big wobble. Big planet, massive planet causes big wobble in the star's motion. And then what is a hot Jupiter mean? It's really close to the star. So the close is not the critical part, like the force of gravity is not the answer to this. But what happens to your orbital period if you're very close to the star? It's short, right? So if it was really short, we could detect that change, and it would make the velocities, the radial velocities, larger, right? So it turns out that hot Jupiters were the first kind of exoplanet to be detected. Okay, that's about all you really need to know. Conservation of angular momentum, we mentioned that already. Big thing collapses to a small thing. It has to spin faster, rotate faster. Condensation theory is the idea that the original gas and dust that formed our solar system collapsed down into a hot mess of a disk, right? And in that disk, little tiny grains of dust would have formed. And as they formed, where did they form, right? So the metal oxide closest to the star, a little further out, silicates, a little further than that, water ice, right? And finally, the other kinds of ice. But those little tiny grains of dust, what made them stick together? You need to know this, right? They're little grains of dust. Why would they stick together? It wasn't gravity, right? That's the important thing. It's not gravity. They're too small. What was it? Static electricity, right? It was when they rubbed on each other, they exchanged electrons. One became positive, the other became negative. They stuck together. So after they clumped together, they smashed together, they would form planetesimals, right? The planetesimals would then bump into each other and eventually form protoplanets, and the largest protoplanets began to make planets, right? So we only got 8, but there might have been more than that originally, right? There might have been more than that. We think that, for example, the Earth got hit by a protoplanet very early on, which gave us the moon. Okay, interstellar dust grain is just dust that's out there, and forget that term. You don't even care, right? It's the dust grain in the original material. But actually, it is kind of interesting because our solar system has more of that stuff than other solar systems, which is kind of interesting. So the core accretion model says that in order for a big planet like Jupiter or Saturn or Uranus or Neptune to form, what had to form first is a terrestrial body. So we think inside of all of those planets is a terrestrial body. And with that body, finally, you've got enough gravity to start grabbing the hydrogen and the helium, right, into your body. Okay, core accretion model. Okay, here we go. This is the longest chapter. The rest are going to be quick, super easy. Okay, determine from the period where the comet came from. I think we've talked about it already. Yeah, question.
I didn't really get the definition of comet.
The comet, which one? Coma?
Yeah.
Coma was the kind of atmosphere that forms when the nucleus heats up when it comes close to the sun, and so it's an atmosphere around the comet. Comet atmosphere. So it makes the comets look fuzzy. Okay. All right. Thank you. Thank you for stopping me. If you need to stop. Okay. Period of comet. What's the benchmark? What do you say? Less than 200 years. That was the short period. They come from the Kuiper Belt, and more than 200 years comes from the Oort cloud. Okay. Identify the ion dust. I've done that already. Okay. Explain using the condensation how the different planets in our system came to have differing compositions. Have I talked about that a little bit? But we could talk about it a little bit more. The main idea is that the raw stuff, the materials that made the planet, would change as you go further from the sun. Near the sun, what's the only kind of grain that you would get? Little metal and metal oxide. And then a little bit further, finally, the silicates would come out. So that's all you have in the inner solar system is metal and metal oxide and silicates. So remember that once the grain forms, it can form anywhere further out in the solar system. It's just that it's too hot to form it any closer than that. And then a little bit further silicates. So you can get it all the way out to the edge of the solar system, but not any closer to the sun. And then similarly for water ice 4.5 AU, that was where it formed, right, outside. Okay, okay, conservation of angular momentum. Okay, we kind of talked about that again, right? So it collapses and forms a disk as it rotates faster. That's conservation of angular momentum. Questions about that? I know it's just super fast, but we got more stuff, right? It's already almost 4. Estimate the location of center of mass. Oh, we just did this. I've done all this stuff for you. Explain the activity of a comet on its elliptical orbit. So what are the 2 words we need to talk about? Closest to the sun, what's the word? Perihelion. Let me use that word more often. Okay, perihelion, closest to the sun. Furthest from the sun, aphelion, right. So when the comet's at aphelion, how much activity is there? None, none at all. Does it have a coma? No. Does it have a tail? No, right? As it comes closer to the sun, at perihelion, it should have the largest coma and the longest tail, right? Because that's the biggest activity. So it occurs at perihelion, all right. Blah, blah, blah. All right, explain the heating and light that are seen when a meteor streaks through the atmosphere, right? So what is it? What's happening? What is that light? It is energy, right? That's a form of energy. What is causing it? The comet has a lot of kinetic energy. When it goes through the atmosphere, what does it do? It compresses the air in front of it. It's called compressional heating. That's most of the heat energy. That heat energy goes into the surrounding atmospheric gases, and they begin to glow, right? That little streak is not the little dust grain burning up. That's not what it is. What it is the atmosphere getting excited by all of that energy. Okay? That good? All right. Blah, blah, blah. M-type, S-type, we talked about that. They came from a protoplanet, probably, right? A protoplanet that broke apart. Describe how the different methods of exoplanet detection work. Okay, I think I already went through this too, right? Did I cover them all? Direct imaging, take a picture of it. It takes a long time. It's also really difficult. The transit method, the planet goes in front of the star. You see a little dip in the curve, and that allows you to indicate the presence of a planet. Super effective. And then the third one, radial velocity. You're looking at the Doppler effect of the star's light. And when you see it changing, you know that the star is wobbling a little bit. So that's the medium effective, the middle effective method. The blue shift redshift. Yeah, Doppler effect would be the name that we give for a blue shift redshift. Okay? And then why is this? Oh, and it was 7. I don't think it's 7. I think I'm wrong about that. I don't think it's 7. It's actually only.
I think there's 7 planets.
There's 7 planets, but there's 3 habitable ones. Yeah, I'm sorry, I made a mistake. Yeah. One more time. The best was the transit method, and the worst was direct imaging, and the medium was the radial velocity method. Okay, so actually it's not 7. I think I messed up. It's 7 planets, but there's 3 habitable ones. Okay, sorry about that, but that's pretty exciting. It means what? Are we going to be able to find other planets out there that are habitable? And the answer is, of course, yes. Yeah, there's going to be. Okay, so that's a good picture, right? Take a look. And it looks like the green zone has only 3 bodies, so I think I made a mistake. Okay, so it's not 7 habitable planets. It's 7 planets, 3 of them habitable, okay? Sorry about that. You can make a note correction. And, oh, yes, I forgot about that. Ryugu. Ryugu is the name of the asteroid. Hayabusa 2 is collecting samples. I think I mentioned that. That's a Japanese Space Administration, JAXA. And it's super cool. So if you go look that up, it's just so funny to watch this. These little landers hop around because the gravity is so small. It's really cute. And then, of course, they dropped down to the surface, collected a sample, then dropped a little bomb and made a crater, and then collected another sample from the interior of the asteroid. It's on its way back home to deliver those to home, okay? And then the planets, okay, I think I might have memorized, okay? The planets, everybody know the planets in order. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. The last 3 spelled sun. That's where people sometimes get messed up. Okay. And then Lagrange positions, I again mentioned already. I did that picture. Okay. And let's see. Okay. All right. Woo! 1 chapter done. Okay. Speed it up, dude. Okay. All right. Chapter 6, radioactive decay. What's that mean? Radioactive decay. Radioactivity means unstable. Unstable atoms are radioactive atoms, right? What does it mean? They're going to change into a more stable form, right? And so we can watch them, but we don't know how long they're going to take. An individual atom doesn't know exactly when it's going to change, only the probability of changing, okay? But if you look at a lot of atoms, it turns out there's a concept called the half-life, which says that it's the time it takes for half of that material to undergo radioactive decay. So yeah, I feel like maybe I should just remind you, because there is a question on your test, so you got to do this, right? If you know the half-life, whatever it happens to be, then you can figure out how much is left and how much is still there, right? So number 1, the matter doesn't disappear, it just changes into a more stable version. So the original material is called the parent nuclide, and the thing that it becomes is called the daughter. So in other words, a daughter is more stable than their parent. All you women out there, you like that, right? And you think it's true, maybe. I don't know. I'm not sure. I'm not sure what to tell you. Could be. Could be. Okay, it was a joke. Sorry, bad joke. Okay, so let's see. I've got bad jokes, even on your review. Sorry about that. Okay, here we go. So I start off with some amount of material. Let's say it's, I don't know, just think of something, Sean. Okay, 8 kilos, right? 8 kilos of some radioactive element. And I know the half-life of this material is like, I don't know, I'm just going to make something up. Half-life is 4 years, okay? 4 years. 4 years for the half-life. So what I'm going to do is just try to think about what happens, right? If you wait 1 half-life, which is 4 years, what will happen to the 8 kilos of this radioactive substance? Well, half of it will change, which means how much will I have left? I'll have 4 kilos of the original radioactive substance. Let's call it A, right? I have 4 kilos of A. But whatever it becomes, which is more stable, I'll have 4 kilos of B, which is the stable daughter nucleus that it becomes, okay? Now, if you wait another half-life, same amount of time, 4 more years, so now 8 years have passed, how much of the original radioactive stuff will be left? So we'll just have 2 kilos of A. And then where did the other kilos go? They turned into 6 kilos of B. And if you wait another half-life, another 4 years, right? Another half-life. Each half-life, it doesn't matter how much you have when you start, only half of it will decay. That's the idea. So if you understand what I'm doing, you can figure out how much is going to be left of the radioactive stuff. 1 kilo of A, and then the other 7 must be B. Okay, so 7 kilos of B. Supposed to be a little larger. All right, you get the idea? So if I ask you, and so the fraction is how much of the original radioactive material is left after 1 half-life? 1/2, right? After 2 half-lives have passed, a half times a half, 1/4, right? After 3 half-lives, a half times a half times a half, 1/8 of the original amount is left over, okay? So if I said to you, how long does it take for 1/8, till there's only 1/8 remaining, the answer would have been what? How many years does it take for 1/8 remaining, which would make 1/8 of 8, which makes 1 kilo? How many years did it take? It took 12 years altogether, okay? Oops, I moved this, whatever. Okay, core, mantle, lithosphere, crust. Okay, here we go. The interior of the Earth, the most inner part is called the core. What's it made of? Metal, right? Iron and nickel are mostly the 2 primary ingredients. But the core is not just the core, right? You want to think about it as having an inner core and an outer core. The inner core is solid, and the outer core is molten, right? It still can move. Outside of the molten outer core, we have the mantle, and the mantle is made of what? Silicate, molten rock, right? It is, the mantle is made of lava, right? Or something like lava maybe, but very fluid type of lava. And the lithosphere is the upper part of the mantle and the crust, and it is considered, it is solid, right? So the upper part of the mantle is actually solid, a little bit solid. Okay, the crust is a very, very thin layer on the Earth, right? That formed probably early on. It's the thinnest part of our Earth structure. It's like skin, right? It's really, really small, like 20 miles thick, right? Considering that the Earth is 4,000 miles in radius, this is very tiny. Okay, crust. I think, I don't know why I'm saying basalt. I think I forgot a word, okay? What's the other word that I forgot? Basalt and granite, okay? I forgot the word granite. Thank you. I should have, I don't know how I didn't notice this. But granite and basalt are 2 forms of silicate that you have to be aware of. So which type of crust is made of granitic material? Lower density granitic material. Okay, it's continental crust. Do you see continental crust? I don't even see that up there either. Oh yeah, I'm failing. It's in the study guide. Is later. Oh, no way. Is it really?
It's right underneath.
I set them the wrong version. Oh, fail. Okay. Okay, so hold on a second. Yeah, I did put it on there. Oh, ooh, I failed once again. Sorry about that. That's funny. So I did update it. I felt like I updated it. Okay. The one that's an. Oh, really? Okay. I better do it. Which one? Oh, the last bullet.
Yeah. On chapter 5.
Oh, it's missing. I changed it. Okay. Okay, so yeah, fine. Okay, that's good. Okay, here we go. But I still didn't put. Where did I put it? I thought you said I have.
Yeah, it's something that I downloaded off of campus.
Oh, huh. This seems to be the one, but anyways, okay. All right. Yours has what? What's
Granite.
it has granite. Okay, I think I felt like I did that, but anyways, let's throw it in there. If it's not on there, make sure it's on yours. Okay, granite and basalt are the 2 forms of silicate. One is more dense and one is less dense. Which is which? More dense. Basalt, more dense. Granite, less dense, right? And if you study geology, you learn why. There's these large crystals that form because it cooled very, very slowly and whatever. You don't need to know that. Okay, so the continental crust is made of granite and the oceanic crust is basalt. Okay, that's the important part. Okay, so how did we learn all this stuff about the interior of the Earth? From seismic activity. In fact, most of it happening in the 50s, 40s, and 50s when we were testing nuclear weapons. Okay, that was when we knew exactly when the earthquakes were going to happen. And we discovered there are two kinds of earthquake waves. One is called the P wave, and the other called the S wave. Why are they called that? P stands for primary, gets there first. It's the primary wave, and S is the secondary wave. And we also discovered that if you go to the far side of the Earth from where the earthquake source is, you can't find any S waves because they cannot propagate through the molten material of the Earth, or the molten core at least. I think they go through the mantle a little bit. But anyway, there's a shielded, there's a shadow region where you can't get S wave. S waves cannot travel through molten material. But P waves do. What's that? Yeah, now I'm not sure. I actually don't think they are completely shielded by the mantle though. But maybe it's the outer mantle that lets them through. Okay, not sure. You don't have to know that either. Okay, but I know for sure that the outer core did not let S waves through, but P waves got through just fine. Okay, there are three forms of heat transfer that you need to know: conduction, convection, and radiation. That's it. There's only three. Conduction requires two objects to be touching, and the heat energy goes, which way does it go? From the hot object into the cool object. If a hot object touches a cool object, the cool object will gain heat, and the hot object will lose heat. Okay, we know this. Convection, there has to be another material to carry the heat energy, and it flows from the hot to the cold, carries heat energy. And so convection happens in lots of ways. Inside of the mantle of the Earth, in the atmosphere of the Earth, in the outer parts of Jupiter and Saturn and Uranus and Neptune, right? It's happening all over the place, but it requires some material to carry the heat, the energy. And finally, radiation. Hot objects glow. The hotter they are, the more light comes out of them. But that glowing is called radiation, right? So that is a way to get rid of energy. Okay, a shield volcano is like the volcanoes in Hawaii. Where do they form? Over hotspots, right? So a hotspot is a thin place. Oh, there's hotspot. Okay, a thin place in the crust where the mantle energy from the mantle can leak up and start to form a shield volcano. But usually the plates are moving. Therefore, you don't get a single volcano, you get a string of volcanoes. So the Hawaiian Islands is an excellent example. So each one of these, you need to remember the example that I gave you. So hotspot, Hawaiian Islands, okay. How about plate tectonics is the idea that the plates, yeah. A plume? Oh, a plume, okay. A plume would be mantle material coming up towards the crust. A plume of material. So as the plume pushes on the crust, what happens? They start to drift. They drift. And so plate tectonics is the idea that the plates are moving because of pressure and forces from the mantle. How does that work exactly? I don't know. And you don't have to know either. But we say that this is what's causing the plates to move. Okay. Continental collision is one kind of thing where two continental plates, continental crusts connect. What happens? They have nowhere to go but up. And so you get the tallest mountains in the world. The Himalaya mountains formed, right, where two continental crusts collide. In the slightly different one, where continental crust hits oceanic crust, who goes on top? Continental crust goes up, oceanic crust goes under. It's called subduction. Okay. Now, it'll get subducted, and a new mountain chain will form there as well, but it's a different mechanism. And eventually, what will happen to the oceanic crust is it'll crack off and fall back into the Earth to be recycled. Okay. So oceanic crust is not going to last forever. It fades away, right? It goes away eventually. Spreading center is where you find two plates moving apart, where any kind of plate at all, moving apart from each other, leaving a gap. And so the mantle material comes up and fills the gap. So it's the freshest young crust that you can find on the Earth. Where do you find it? The Mid-Atlantic Ridge is an excellent example, the best example to use. Okay, so that's where you find a brand new crust, like literally this week, this day, right? Old, it's very fresh. All right, troposphere, stratosphere, mesosphere, ionosphere, those are the levels of the atmosphere, about 100 kilometers worth. Right? At 100 kilometers, we say that you've reached the Kármán line and you are now in space. Anybody who goes above that is called an astronaut, right? Anyway, so the lowest level is the troposphere. That's where all the weather is. So all the clouds, you and I live here, right? Troposphere, this is where the weather is. Okay, troposphere, lowest level. Yes. One more time, sorry. All right.
Fly in the troposphere. Do they fly above it?
Oh, do they fly above the troposphere? No, we don't fly above the troposphere. No, planes don't fly above the troposphere. No. Do they? Yeah, in. It's the first like 20 miles. Yeah, we don't fly above like commercial airlines. Oh, so okay, planes can potentially, but that's like top secret, military type of stuff. But a typical commercial airline is much, much lower in the troposphere. Yeah. Okay, you get above the troposphere, and so what is the primary component that is important to us? Is the water exists in this layer. Most of the water is in the troposphere. Okay, water is important as a greenhouse gas. Number one, greenhouse gas. You guys knew that, right? And that is why it absorbs. Why infrared light doesn't get through our atmosphere very well, because of all the water in the atmosphere. So the greenhouse effect primary component is water in the atmosphere. Okay, that's not something you and I can control though. Okay, the next level, stratosphere, has the ozone in it, right? So that's the stratosphere, the ozone layer. Good thing. What does ozone do for us? It blocks ultraviolet light from coming through. So we get some, but not as much as we would if without that ozone layer. Mesosphere, middle layer, that's where the meteors will burn up, right? That's about all I can say. I don't have anything else. Ionosphere is the highest level. It's the electrically charged part of the atmosphere. Lots of interesting electrical stuff. Ozone is, we just mentioned, absorbs the ultraviolet light from the sun. The greenhouse effect is the idea that visible light can come through the atmosphere, but then the heat energy that the Earth is trying to radiate can't get out, and so it stays warm. And so the idea is you don't want to say greenhouse effect is bad, because that's not true. Okay, greenhouse effect is good. It makes life really wonderful here on Earth. But too much of it is bad, right? So you want a certain level. We don't want to keep making it go up. So the three important greenhouse gases that we talked about, number one, water. Can't do anything about that. Methane, we can do something about that. That's number two. And then number three is carbon dioxide. We can do something about that too, right? So our use of fossil fuels is making the carbon dioxide level go up in the atmosphere. We can see that it just keeps going up and up and up. We need to stop that going up and up and up thing, okay? So we need to look at ways to suck it back out of the environment, maybe. That's another idea. Could be money though, right? Could cost money. So if somebody says we can do it, but you have to raise your taxes, how many people would pay more taxes? If we could make the environment better and the climate not change so radically, it would be worth it, right? So it turns out we can do it. We have the technology, and it's also getting better. All right, keep going. Magnetosphere, what are we talking about? The magnetic shield around the Earth is called the magnetosphere. Okay, we have a magnetosphere, a sphere of magnetic field, and it protects us from what? Primarily the solar wind, right? The sun is trying to pelt us with little tiny charged particles. When they hit the magnetic field, they spiral around and give us the most beautiful display called the auroras, right? The aurora borealis, northern lights, and aurora australis, the southern lights. How do you get the magnetosphere? Well, you make it with a magnetic dynamo effect. We think that charged material is circulating inside of the Earth. So we think that where is the magnetic field generated? In the molten outer core of the Earth. That metallic stuff conducts electricity and it's circulating, and therefore it gives us the magnetodynamo effect. So all planets that have a circulating charged material will have a magnetic field. Solar wind is charged particles, mainly hydrogen and helium, right? Particles, charged, coming from the sun. Electrons, neutrons, okay, some other stuff. Aurora borealis, aurora australis, I just mentioned, right? Northern and southern lights. Okay, tides. What causes the tides? The moon and the sun, right? The moon and the sun. Actually, I was on the wharf last night, and they have a plaque, and it was actually really good. I'm like, well, that's cool. From the Museum of Natural History. Like, good, great, okay. The moon and the sun, which one's more important, the moon or the sun? The moon. So the moon determines where the high tide will be. That's it, right? Where if the moon is above you, what do you have? High tide, right? If the moon is on the far side of the Earth, though, you also have a high tide. So the key thing is, let me draw a little picture, right? You guys, we'll do the whole thing real quick, right? we have 2 high tides per day, approximately 12 hours apart. 2 high tides, where are they found? Where the moon is, right? And also across the Earth from the moon.
Oh, that's interesting. I understand the first one.
Yeah, actually, so you understand why? Because it's being pulled on stronger, right? So you can kind of think of on the far one as the Earth itself is being pulled stronger than the water is, and so it has a bigger radius as an effect of that, or something like that. Okay, so we'll talk about it. Give me a second. Okay, so Earth and Moon. Okay, so Moon, Earth, right? And the idea is that I forgot something. Okay, so we'll have to put sun somewhere too. But anyway, so this is a high tide. So there's going to be a bulge of liquid over here and also over here. So this line determines where the high tide will be. So I think it's probably useful just to think of the moon is pulling on the Earth with different strength force of gravity on the near and the far side. That difference in the force of gravity is known as the tidal force, right? It's a stretching force. So again, the near side is feeling a little bit more gravity, and so the bulge of water makes sense here. But in this one, if you compare the center of the Earth with this edge, the center of the Earth is feeling a stronger force of gravity. It's kind of leaving this liquid behind a little bit, right? It's being flung out, something like that. I wouldn't worry too much about it. It's pulling the Earth apart. Okay, that's the tidal force. Now, if the sun is also lined up with it, then what do you get? Right? If the sun is going to be lined up right here, what phase would the moon be right here? That's a new moon. And if it's also on the other side, new or full, you get this effect. And what do you get? Called the spring tide, right? So the tide is even higher than before, which, by the way, leaves even less water here. So you have a higher high and a lower low, right, as a result. So higher high, lower low is called the spring tide. And then in the case where the moon is not in that position, I should have put spring. If the moon is actually on this or this side, right, first quarter and third quarter, where's the high tide in this case? Well, it's with the moon, right? The moon determines where the high tide is going to be. But the sun is pulling in a different direction. So it's pulling away from what this high tide would be. It's making the high tide lower and making the low tide higher, right? So what it does is when you get the neap tide, right? This is going to be neap tide. So in a spring tide, you get big changes in the tide levels, right? But the neap tide is little tiny changes in the tide level. Okay, actually it should be the same period. I messed up a little bit on that, but that's the right idea. Okay, little tiny wiggles, little tiny changes, spring and neap. So how often does it happen? How often do you get a spring tide? Twice a month, right? And how often do you get a neap tide? Twice a month, same thing. Okay. Tides, tidal forces, spring tide, neap tide. Tidal locking. Tidal locking. Is Earth's moon tidally locked? Yes, it is. And that means that one face is always facing the Earth. And the reason why, do you guys remember? Called a synchronous rotation. It takes how long to rotate? The same amount of time as it takes to make a revolution, 27.3 days, that's right. And that's what tidally locking is. When the rotation period is the same as the orbital period, that's tidally locking, okay? So when we ask it in the future about Mercury, is Mercury tidally locked? Not yet. It will be. Okay, real quick thing, craters. What's a crater? A hole in the ground, yeah. What made it? An impact, right? And some craters are fresh, some are old, right? We can actually figure that out because some are really circular when you look at them, and others you can hardly see that it's there, right? So if we look at the moon, we see different kinds of terrain. And in fact, there's highlands and lowlands. And let's look at the moon. Okay, moon map, right? There you go, moon. There it is, that's it, moon. That's all I need, just a picture of the moon, right? So when I look at this picture, I can see everything I need to see, right? So we have the lighter parts right here, everything light is kind of grayish looking. There's crater after crater after crater. This is old, right? And in our solar system, whenever we see a body with lots of craters, we know that that surface is old. When we look at the Maria, which are the dark areas, we can see that there's hardly any craters at all. That means they formed much later, right? There's no impacts that happened after that. And they happened actually as a result of big impacts on the moon, right? So all right, so the Maria, the dark, and the highlands. So highlands are old, Maria are young, right? They come from flooding. Okay. Oh, right here. Right here, right here. There we go. Okay, and we think that most of the cratering occurred very early, about 4 billion years ago, between 4.1 and 3.8 billion years ago, called the late heavy bombardment. Okay, giant impact hypothesis, what does it mean? Where did the moon come from, right? A Mars-sized protoplanet slammed into the Earth and merged with the Earth, but a big chunk of it and the Earth was flung off and formed the moon, right? It went into orbit for a while and formed the moon. We think that that's the best hypothesis, okay? Some of the others that we didn't like are called capture and the fission hypothesis. We don't like those. All right, to be able to determine the amount of radioactive substance. Actually, can you tell me if I leave anything off of the new study guide? Okay, thanks. Determine the amount of radioactive substance left after a certain small number of half-lives. Okay, we did that. Describe how plate tectonics lead to. I think we've done that too, right? Describe how the greenhouse, describe the structures of the Earth's atmosphere and what each layer does. I think we did that, right? Describe how the greenhouse effect works. What compounds in the atmosphere are most responsible for it? What is the basic idea? Greenhouse gas, they don't block visible light, but they do block infrared light from getting out, right? So the sunlight comes in, turns into heat energy, doesn't make it out, so it gets warmer. Okay. Describe how the magnetic field of the Earth functions and protects us from the solar wind. It's generated inside the outer core of the Earth, wrapped around the Earth. Where's the Earth magnetic field the strongest? At the poles, which is why the auroras are brightest at the poles. That's where they do the best job of diverting the charged particles. Okay, compare the relative strength of the sun and the moon on the Earth. Gravitational force. So what's the gravitational force? Which one is bigger on the moon, the sun or the moon? I'm sorry, which one, the sun or the moon, has a stronger gravitational force on the Earth? The answer is the sun, right? The Earth goes around the sun. But which one has a greater tidal force? The answer is the moon, right? Because it is so much closer, it stretches the Earth much more effectively. Okay, why do the capture and fission hypothesis do not fit observed data? Capture means what? The moon was captured, and it would be totally different than the Earth, but it's not. It's very similar, okay? Fission, the moon spun around, the early Earth was rotating really quickly, and it just flung out, and then the material of the moon would be identical to the crust of the Earth, but it's not. It's really more like the bulk of the Earth. So which model is accepted today? The giant impact hypothesis, okay. Describe the features of the moon formed and what they can tell us about the relative age. Okay, so the Maria formed when big impacts happened, broke the crust open, and then magma from inside of the moon flooded up through those cracks and filled in the valleys, the low-lying areas. So they were once the valleys on the moon, okay? And so they are younger because they formed after all the cratering stuff. Okay, you don't have to know the sizes, forget that. The orders of the layers you need to know. And you need to know the lunar rotation period is equal to 27.3 days along with the rotation period. Rotation and orbital period, okay? All right, number 7, chapter 7. Okay, they're getting shorter and shorter. Oh yeah, definitely, much, much shorter. Okay, so chapter 7, and if you're coming in later, if you guys make sure you sign the attendance sheet at some point afterward, be okay. Okay, so talking about all the planets, all the terrestrial planets, they originally were, in what state did they have to be in order for differentiation to occur? They had to be molten, right? So the early stage, when you smash together all of these materials, they heat up, right? This is actually a natural consequence of gathering material from far away. What kind of energy do you have if you're far away from the center? It's called gravitational potential energy. When you slam it together somehow, it heats up as a result of changing the energy from potential into kinetic, right? Thermal energy. So if it's nice and hot, then you can get differentiation, which is, again, we already did this, but separating by layers with different densities, right? So the most dense goes to the center. That's where the iron and stuff like that goes, and then silicates and so on. Okay, so cratering, so cooling, sorry, that's important, right? How do you cool off? How does any body in space, in the vacuum of space, cool off? There is only one mechanism. What is it? Radiation. That is how you cool off. There's no other way because there's a vacuum. There's no way to get rid of the heat energy except by radiation. But anyways, you cool off a little bit and you get a skin on top. And that skin is called the crust. So crust forms very quickly. And then you get bombarded and you get cratering, right? If the cratering leads to cracking open the crust, then the magma can come up and fill the spaces, and that's called flooding. And finally, what do you need for weathering to take place? You need an atmosphere, right? So anybody that has atmosphere is going to have weathering. If you don't have atmosphere, you're not going to have weathering. Is there weathering on the moon? Our moon? None. So when we see the moon today, there's any of the effects that we see are all based on collisions of some kind, right? Cratering events, not from weather. There's no erosion like we have on Earth or other bodies with an atmosphere. Okay, Wrinkle Ridge happens anywhere you have a body, form a crust, and then what happens? Wrinkle Ridge, who remembers? Skin doesn't fit. Yeah, so which part cools? The core cools and shrinks in size as part of the cooling process. So now the original skin doesn't fit, right? So what does it do? It folds like a Shar-Pei puppy, right? Okay, if you think of that. Anyways, the folds are called Lobate Scarps. That should be on there. It's not on there. Okay. Wrinkle Ridge, another word is Lobate Scarp. Do you want me to write that down? Raise your hand. I want to write that. Okay, thank you. Okay. I got to write that down. Okay. Lobate, L-O-B-A-T-E. Lobate Scarp. Okay, so a wrinkle ridge is a cliff or a feature that forms because the skin no longer fits. And so the only way it can fit on the smaller size core is if it folds itself over a little bit. So Wrinkle Ridge is also called a lobate scarp. A scarp is a cliff. So lobate scarp is the technical name for a wrinkle ridge. Lobate scarp, that's the wrinkle ridge, equals wrinkle. So where do we see these? Well, we first found them on the moon. Actually, we first found them on the Earth moon, as a matter of fact. They have them there. And then we also found them on what planetary body? On Mercury, okay? And so even though you're going to remember that Mercury is dead, right? Completely dead? No, not completely dead. It turns out NASA has seen new lobate scarps forming. So what does it mean? The core is still cooling off. It's strange, but it's true. So it's almost dead except for that tiny little bit of change that we see at the surface. So we're going to say that Mercury is mostly dead, but not quite completely dead. Okay, fossil magnetism, again, an idea. If you don't have what? You can't have a magnetic field. Molten conducting material. If you don't have molten conducting material, you cannot have a magnetic field. So does Mercury have molten conducting iron in its core? Not anymore. It's too small, right? The moon doesn't either, right? It's too small. So it's solidified. So what does it mean? You can't generate a big magnetic field from the magnetic dynamo, but the crust may have materials that could capture the original magnetic field. Actually, I didn't talk about this, but one of the ways that we know that the Earth magnetic field has changed is by analyzing the oceanic crust. And we find out that as it solidified into crust, it locked any of the iron stuff, which is magnetic, locked into the orientation of the field that it felt. And so if you study the field, they switch periodically in the Earth, right? So we've actually figured out that the Earth has a switching magnetic field about every 20,000 years, or maybe a little bit longer. Anyways, we don't know when it's going to happen. But so fossil magnetism is the idea that the crust can capture the original magnetism of the body. And so it's still there in a very small way, but it's not anything significant. So both Mars and Mercury have stuff like that. Okay, fossil magnetism. No magnetic dynamo effect, but still some original magnetism still there. Okay, tidal synchronization is the idea that the tidal force causes the rotation of the body to speed up or slow down. Slow down until it matches the rotational period. Okay, so Mercury is not quite there yet. It's in a 3 to 2, 2 to 3, depending on how you say it. So 2 to 3 orbital rotation resonance, right? So it takes 2 revolutions to equal the same amount of time as 3 rotations. Mercury orbits the sun every 88 days, and it rotates every 59 days. And so that happens to be, if you get the real numbers, a 2 to 3 ratio. So it's not quite tidally locked yet, but one day it will be. Okay. All right. So that's called a resonance. All right. Retrograde rotation. Yes. Question. Okay. So Mercury has a 2 to 3 orbital rotation resonance. It's called. Tidal forces causes it to slow down its rotation until it matches the revolution period. Okay, so when the rotation period matches the revolution period, it's tidally locked at that point. So it's rotating in less time than it's taking to orbit the sun. When it slows down to 88 days, right, the time it takes to orbit the sun, it will then be tidally locked. That make sense? Got it, okay. Retrograde rotation, is there any planet that does that? And the answer is just one. Which one? Venus, all right? You're thinking about Venus? There's not a lot of stuff on Venus, but anyways, a couple things about, actually it's coming down here, but Venus has a retrograde rotation, or you can flip it over. You could say that it's been flipped over almost 180 degrees or whatever, 170 something. What? 177, well, thank you. I should know that, but anyway, thank you. Okay, so it's almost flipped upside down, and we think that, actually, how would you explain the flipping? Probably a really big protoplanet. Venus doesn't have a moon, right? Where did the moon go, right? So I don't know this. We don't know the answer, but it would be a good hypothesis to say that a moon smashed into Venus and caused it to flip over. That would be okay, right? What's that? Yes, right. No, that's not possible. So all the planets would have originally had no tilt and would all be rotating in the same direction as they orbit around the sun because of conservation of angular momentum. The fact that Venus is flipped over and seems to be rotating the other way is strange, right? No one else does that. Everybody is in the game, right? Going the same direction. Okay, a couple of things. Caldera is a hole in the ground that looks like a crater, but is not a crater. It's a caldera. It's a place where lava or magma would have receded. So it originally pushed up, leaked out, and formed this thing called a corona. This is on Venus, right? These are on Venus. They're big pancakes of magma that flowed out of a volcanic, some kind of a volcano, not erupting, but just kind of oozing out and making like this puddle. And then when the magma subsided, the ground sunk down and you got a crater there. Or it's not a crater though, it's called a caldera. Okay, it looks like a crater, but it's not a crater, okay? The pancake of magma went out and spread. That's called a corona. And then as the magma receded and stopped pushing out again, it actually, the ground was sunk in where it originally was pushed up a little bit, and that became the caldera. So it's when the magma recedes. So there's a plume of magma that then recedes away, and that leaves the caldera. Okay, Olympus Mons, anybody know what planet we're on? That's Mars now. Okay, there's more stuff with Venus, but apparently they're not vocabulary words, okay? Right, definitely you need to know a few things about Venus, but we'll get back to that. Okay, the words, Olympus Mons, the largest volcano in the whole solar system. There's nothing bigger that we've seen, okay? Valles Marineras, right, the Mariner Valley. It's this giant 2,500 mile long, 100 mile wide, 4 mile deep, like a Grand Canyon across the face of Mars. It's huge. How did it form? We don't know, right? We don't know. Could be one of its moons, could be a comet, could be a bunch of things, but we don't actually know the reason. When we go there and we start sampling material, we'll know. So next year, when the first colonists are living there, that was a joke, sorry. So okay. Couple years from now, 2025, I don't know. Okay, blueberries, what's blueberries? These little tiny crystals, yeah, blueberries. Little tiny hematite iron oxide minerals that formed. They have to form in a wet environment, and we found them immediately, like day one. As soon as we started looking around on the surface of Mars, we found them. So we knew that Mars was once wet at the surface. It's not wet at the surface anymore, right? We'll talk about that in a few minutes. Okay, the Noachian, the pre-Noachian, the Noachian, the Hesperian, and the today Hesperian period. Which one was good for life? The Noachian period. That was the time when you had an atmosphere, when you had liquid water at the surface. It was warm, right? So there was all the stuff that we would think life would need. Amazonian period today is very cold and very dry, very small atmosphere, no magnetic field, right? And that's really the problem. Okay, so here we go. Be able to describe. I told you about this. The features of Mercury's surface and why NASA announced last year it's still alive. The answer is new Lobate Scarps, right? New wrinkle ridges had formed. They took pictures before with another mission called Messenger, and then, I'm sorry, another one before that. Then Messenger came along. But anyways, either way, they took a picture. A new Lobate Scarp was there that wasn't there before. And so they declared, hey, it's still alive, still shrinking. Hey, number two, explain how Mercury can be seen to have a thin layer of hydrogen and helium near the surface, but it's not an atmosphere. Where did it come from? From the solar wind, right? So Mercury can trap it for just a little while. And this is the hydrogen and helium that is part of the solar wind. But it's not really an atmosphere. It's just going to go away very, very quickly. So it has nothing permanently. There's no weathering taking place on Mercury, right? No weathering taking place. So lots and lots of craters, right? Old surface. Okay, what are the similarities and differences? Okay, similarities. Core, mantle, crust. What else? Iron. Big core. Differences. Not all of them have moons. Not all of them have what? Not all of them have magnetic because they're small, right? So the big ones still, oh no, that's not true. The only one who's got a magnetic field is really Earth, right? Venus has lost its magnetic field. Mercury, Mars lost theirs, okay. So yeah, that one, you know, there's so many things too, actually, I don't know. What else, anybody, I'm thinking, missing something? Similarities, they're made of the same kinds of stuff. That's a big similarity. What's the difference? The sizes, the masses. Venus and Earth are about the same size. How big is Mercury? Less than half of the size of Earth. How about Mars? A little more than half, right? But they're both pretty small, Mercury and Mars, okay? That's why we think Mars-sized objects smashed into the Earth, making the moon, right? So Mars is pretty small. Okay, so other than that, I don't know. My Mercury do not have strong magnetic fields. Why does Mercury not have a magnetic field? It cooled off already. How about Mars? Same answer, cooled off already. How about Venus? Is it cool inside? No, it's hot inside. Venus is super hot, right? And its core must have molten iron, but it's rotating incredibly slowly, right? So what is the rotation period? Longer, it takes longer to make one rotation than it does to orbit the sun. So 243 days for rotation, 225 for revolution. Anyways, it's just really slow rotation, so you can't get the dynamo effect with that. Okay. Why does Mars, okay, what's the evidence that Mars was once a wet world? Well, first of all the modern data, by the way, you should know about, that there's ice everywhere on Mars, that we can see it 20-mile thick ice sheets at the poles. We also, NASA has detected liquid water underground, 20 miles underground or something like that. So we know that there's still water there, maybe 80% of the original water. So there's no longer any doubt in anybody's mind that Mars once was really wet. Okay, it's just not true anymore. We find features like riverbeds, we find, you know, all kinds of evidence for that. But it did, in fact, dry out. Okay, so why does Mars have the largest volcano in the solar system? What's special about the Mars crust? Super thick or not very thick? Which one? Super thick. Otherwise, it couldn't support such an enormous volcano. It's the size of Arizona. This is an enormous volcano. If you took that and put it on Earth, it would sink down into the mantle. It could not exist. Our crust is too thin, right? So this is a sign of why we don't think Mars has any plate tectonic features at all. There's no Himalaya-type mountains. There's nothing like that. Subduction, hotspot. Oh, there was a hotspot. That's it. Hotspot, right? The volcano. But other features were not seen. So thick crust, right? And slow-moving plate. It's one hotspot in one place for billions, maybe not billions, maybe millions and millions of years. Okay. How do we see seasons on Mars? How do we see them? Does anybody remember? I don't know if I talked about this too much. The poles, right? The ice caps, right? So you can see ice sometimes, and then ice goes away. So in the winter, you get ice at the poles. What kind of ice? Carbon dioxide, dry ice. Where did it come from? From the atmosphere of Mars, which is pure carbon dioxide. It gets deposited in the winter time, and then what happens in the summertime? It goes back into the atmosphere. It sublimates back up into the atmosphere. Okay, so it's there, and then it's gone, right? So Mars has seasons because it has an axial tilt of about 25 degrees, right? Very similar to the Earth. Describe the sunset on Mars. Just a tiny little thing. What color is it? It's blue. Because the particles are larger, they scatter red light, which is why the sky is red on Mars. And then when the sun is setting, of course, all the longer wavelengths are gone and only the short wavelength blue makes it through, and we see a blue sunset. Okay, the rovers have shown us that. Okay, terrestrial planets all begin with CO2. Only the Earth changed. What caused it to change? So CO2 is called a primary atmosphere. What changed the atmosphere on Earth? Life, living things, right? They took that carbon dioxide in and created their structure, right? The shells, the bodies, right? Trees are doing this today, right? They take the carbon dioxide and water in. They build complex carbohydrates, right? That's what carbohydrate means. Carbon dioxide and water molecules linked together to form chains, and that's their structure. So what happened is the nitrogen and oxygen were just a trace originally on the Earth, but once the life began to suck the carbon dioxide out of the atmosphere, it left behind the nitrogen and oxygen. What is the atmosphere of Earth today? You're supposed to know that. What percentage? 78% nitrogen, 21% oxygen, 1% argon, right? And yeah, okay, but everybody else, so Venus still is pure carbon dioxide and Mars is still pure carbon dioxide. Venus, much more, Mars, much less. Okay, so here we go. Tell the story of how Mars became cold and dead. Step number one. Anybody remember? Step number one. Cool off the core, right? Step number one. You're a small planet. Your core cools off very quickly. Because it cools off, what happens? Your magnetic field goes away, right? So step one, cool off the core. Step two, because you lost your core liquid, your molten metallic core, you lost your magnetic field. Okay. Now the solar wind comes blowing in and there's nothing to push it away. And so it blows the atmosphere away. So the solar wind does that. It energizes the atmosphere and causes it to escape from the planet. The magnetic field protects you from that. So would it happen to Earth without a magnetic field? Yes, eventually, right? We have a pretty good atmosphere though. And then finally, what happened? Because you don't have an atmosphere, what happens to liquid water at the surface? It can't exist as liquid anymore. It has to evaporate. And so you lose all the water. You now no longer have protective layers of atmosphere to provide you with a greenhouse effect. And so you are cold and you are dry. Okay? Cold and dry. All right, got that? Memorize the 5 stages in the evolution of a terrestrial planet. Stage number 1. You try to memorize if you can, right? Stuff gets thrown together, really hot mess. What happens? Separates by layer, differentiation, right? That's the first stage. Hot mess separates by density layers, differentiation. Then cools a little bit and forms a crust, which then can be impacted. So what's the second stage? Cratering happens, right? Now, if the events are really powerful, they can actually crack open the crust and magma from inside can come up and fill in the valleys called flooding. They call it flooding, right? Flooding. Okay, you got flooding. What are we up to? Oh, is that it? How many stages? What's 5?
Weather.
Did I do 4 already? Differentiation. Oh, cooling? Was that one actually? Oh, I messed up. I forgot cooling. Okay, cooling, forming the crust. And then comes cratering, then comes flooding, then comes weathering. Okay, great. Thank you. Thank you. All right, the tilt of Venus, 180 degrees. The tilt of Mars. What about Venus? I'm missing some stuff on Venus. What's Venus's atmosphere made of? I'm missing some stuff. I don't know why it's not here, but you should know this, so I'm telling you right now. What's the atmospheric pressure at the surface of Venus? 90 atmospheres of pressure. What's the temperature? Hot. Real hot. Like, actually, I'm getting different numbers. It's like 700 degrees. It's hot enough to melt lead. It's really hot, inhospitable. What are the clouds made of? Little droplets of sulfuric acid. Does it rain on Venus? It does, but does it hit the ground? Never makes it down to the ground. It's too hot, so it goes back up to the cloud layer. So it's really toxic environment. Okay, really bad. Have we ever had a spacecraft land there? The Venera missions made it to the surface from Russia. Okay, from Russia with love. The rotation rate of Mars. Anybody remember? That's a movie. It's an old movie. Rotation rate of Mars. 24 hours and 37 minutes, just a little bit longer than the Earth rotation. And the tilt is 25 degrees. That's just remarkable. It's just a coincidence as far as I know. Unless we find out that aliens made us both. And then the answer is the aliens made it. Okay, that was a joke, sorry. All right, here we go. Outer planets. Stellar occultation. Ooh, I know what we're going to talk about here. Stellar occultation. Stellar meaning stars, occultation, blocking the light of the stars. Okay, we discovered something interesting when we watched the planets, actually all the planets, Jupiter, but Saturn already had those big rings to see. But Jupiter, Uranus, and Neptune, we watched them blocking the light of the stars, and we learned something really remarkable. Even when the planet was not there yet, it turns out just before the planet got there, the light of the star would be blocked. And you're like, what? How is that possible? And the answer is there were rings blocking the light of the stars. So we discovered the rings of Jupiter and Uranus and Neptune by the fact that they block the light of the stars. We hadn't seen them, right? They're very dark. And so I don't know if you guys have to leave, you got to leave. But why is it that they're so dark? They have high or low albedo. Very low albedo. They're made of dirt, right? They're dirt and metal grains, silicate grains. They don't reflect light well. What about Saturn's rings that make them so reflective? They're made of ice, mostly made of ice. Okay, water ice. Okay, so something special happens because of their big size, their big mass. The hydrogen that's compressed inside of Saturn and Jupiter takes on this form called metallic hydrogen. And why do we need that? What is it good for? Generating a magnetic field. Okay, the metallic hydrogen layer inside of Jupiter and Saturn is creating the magnetic field. And it's really strange stuff. I told you about an experiment. They seem to have created it on Earth in this really special device where they created incredible high pressures. They saw something very shiny, and that we think is metallic hydrogen. Okay, belt and zone circulation, what is that? Yes, question. Stellar occultation is the idea that when the planets, Jupiter and Uranus and Neptune especially, when they block the light of a star, we saw something very curious. Just before they got there, the light of the star was blocked, even though the planet wasn't there yet. And this is how we discovered that those 3 planets also have ring systems. But the ring systems are very dark. We can't see them. And so the rings, the stellar occultation allowed us to see that there are rings around Jupiter, Uranus, and Neptune. It blocked the light of the star before the planet got there. Okay. All right. Belt and zone circulation. Again, I had to tell you that the book was wrong. I hope you made a correction in your book. But you don't need to worry too much about that, but you should know which is which. So if you look at the outer layer of Jupiter, you can see these stripes, right? You see these stripes. So the stripe pattern across the surface of, so this is Jupiter's surface, we see a stripe pattern. We see these darker these darker areas, which are called the what? The belt, right? So we have these darker areas, and we think that those are descending gases. They're dark, right? The dark belts. Okay, and then right next to them are the light-colored, cloudy regions, which are called the light zones. Light is actually the an adjective I'm using. But those are upwellings in the atmosphere. But anyways, this is material that's flowing in a convective cycle, right? So this is called the convective fluid, just like in the core of the Earth, or not in the core, in the mantle of the Earth. Okay, so it's convection taking place in Jupiter, Saturn. Actually, it turns out in all of the giant planets, it's happening, right? So why is it happening? Heat is trying to get out, and heat is trying to get out. It turns out nature finds the most efficient mechanism. And in the outer part, this is more effective than conduction, right? In the inner part, conduction is more effective. But there, you get out there, it's convection. Okay. Did I answer the question, kind of? Okay. Great red spot, big storm on Jupiter. Great red spot. And it's been there for hundreds of years, okay? So something is energizing it. It's not dying away like storms do on Earth. On Earth, the energy doesn't stay concentrated, it dissipates, right? So eventually storms stop. But on Jupiter, it's being pumped with more energy every day, which keeps it going. So it may last forever, although it seems to be getting smaller, right? And in fact, we found other ones, not just the Great Red Spot. There's other little red spots as well. Why is Titan up here? Oh, sorry, with that. Something we skipped that. How many moons does Jupiter have? Before I move on. 79 moons, right? What are the biggest moons called? There's 4 of them. Io, Europa, Ganymede, and Callisto, right? Okay, so I think they come down a little bit later, but I just want to make sure. Okay, now jumping to Saturn. Actually, Jupiter rotates in a time of about 9.5 hours, right? That's a pretty fast rotation. And Saturn, now I'm jumped over to Saturn, oblate sphere. The shape of Saturn, not sure exactly why. I don't know why it's more oblate than Jupiter, because it actually has a rotation of about 10.5 hours, but we definitely notice that Saturn is more flattened. Okay, so instead of being a perfect sphere, the rotation causes the equator part to bulge out a little bit, and that's called oblate, right? That's the word that we use. Titan is the biggest moon of Saturn, and what's special about Titan? Got to know this. It has atmosphere and really interesting structure, right? Very interesting. So it has, yes? Oblate is the idea that it's not a perfect sphere, but around the equator, this is stretched out a little bit. So it's kind of ellipsoidal, a little flattened, but it's because of the fast rotation that's causing that to happen. That's Saturn, yeah. It's actually true in all of them, including the Earth, but it's most obvious in Saturn. And I don't know exactly why, so don't worry about that. Oh, Cassini Spacecraft. Cassini was an amazing spacecraft that orbited Saturn for 13 years, did way too much stuff, and it dropped the Huygens probe, you're supposed to know that, onto Titan. So this is how we learned as much as we did about Titan. Enceladus is another moon of, okay, I think it's gonna be down here. Should I just tell you right now what's important about Titan? Anybody? Yeah, okay. So it has an atmosphere. How does it have an atmosphere? I think that's a really good thing to know, and I think that you can figure it out if you think about it. What makes Titan possible? Why is it possible to have an atmosphere on Titan? There's 2 good reasons that I think you should think about. What is it? The gravitational force. It's pretty big, right? It's a pretty big moon. It's not the biggest moon, but it's a pretty solid sized moon, right? So being larger means it has a greater gravitational force. So we're trying to figure out, how do you keep the atmosphere from flying away? Which way? I don't know if I told you. I don't think I told you in the class, but it has a nitrogen atmosphere. This is kind of interesting. Nitrogen atmosphere with a little smog layer, which I didn't get into, but that's very interesting. Too bad I didn't get a chance to tell you that. It's pretty cool. But anyways, nitrogen. So what about that? Okay, it's large. Bless you. And it is incredibly cold. So the atmosphere molecules have very little kinetic energy, not enough to escape from the body. So that is why it has an atmosphere, which is kind of interesting, right? So it's big enough, and it has an atmosphere because it's really cold. Okay, really cold. All right. Enceladus is special because, that's you again. Okay, it's an icy moon of Saturn, just like Europa is an icy moon covered with a sheet of ice, right? And Enceladus has these jets of water, cryovolcanoes, that are actually going into orbit around Saturn, which is really cool. And it's making one of the rings of Saturn called the E ring, okay, which you're supposed to know about. Okay, there's a really interesting thing. Again, I didn't talk about it, but Phil talks about it. Some of the rings in Saturn are being held in place by little tiny moons called shepherd moons. And we think that they are actually developing, they're keeping it from straying, keeping it kind of in one little ringlet, okay? Orbital resonance is the idea that the rings that are in a resonance are going to tend to be disturbed. And so, is that right? Yeah. If they're in a resonance, they're going to be disturbed and they won't be able to stay there. So orbital resonance is the concept that if you are being tugged consistently, you eventually get tugged out of orbit. So you won't be able to stay. Roche Limit is really critical, and I didn't talk about it, so you guys are going to get it right now. It turns out if you're too close to a planetary body, the tidal force of the body will rip you apart, okay? So I want you to know a couple of things about Saturn. The beautiful rings are actually going away, okay? So you should know that the rings of Saturn have not been there since Saturn was born. They could not have been born with Saturn, okay? Why not? Because Saturn and Jupiter are radiating lots and lots of heat energy. Those ice crystals should be sublimated away. In fact, they should probably not last more than a couple 100 million years, maybe, okay? So anyways, the Saturn is not going to have rings forever. Well, maybe, I don't know, I'm not sure about that. I do know that the rings were not formed with Saturn. Okay, so the size of the body, we'll call that R, and the Roche limit is the distance at which the tidal force is strong enough to rip a loosely connected body apart, like an asteroid or a comet, okay? So the distance is 2.4. So the distance is 2.4 radiuses. It's called the Roche limit. So now, if you are a solid chunk of metal, you don't care about this limit. It's not important to you. But if you are just a loosely connected body, like an asteroid or a comet, and you get a little bit too close right here, what happens? Your tidal forces of Saturn or whatever are going to rip you apart into pieces. So if I had to tell you where the rings come from, I would say that this is where the rings came from. A Kuiper Belt object drifted too close to Saturn and got ripped into shreds. So here's the best part of the story. This Roche limit is theoretical. However, all of the main rings of Saturn are within the Roche limit. All of the main rings are within the Roche limit, just inside the Roche limit, which gives it some credence, right? It's kind of a cool story. Are all of the rings within the Roche limit? No, there's a really important fuzzy one right out here called the E ring. They all have names according to when they were discovered, but the E ring is fuzzy and it's outside the Roche limit, but we know what's causing that. What is right in the middle of the E ring? The E ring, what's right in the middle of the E ring? Enceladus, with its geysers squirting liquid so fast that it goes into orbit, and those little water droplets become ice crystals that are forming Enceladus. Okay, Enceladus is making the E ring. Okay, so those are the main things to worry about with that. Okay, so we got Roche limit. That's where. So in other words, Saturn's rings are going to go away, but then again, we could get new rings, right? Actually, here's another cool thing. We could end up seeing bright rings appear around Jupiter, Uranus, and Neptune at any time. If somebody gets too close to them, then they will break apart the body and make beautiful rings. Okay, so Saturn E ring I just mentioned comes from the planet or the moon Enceladus, okay? Miranda is the one, okay, you guys, this is all learning on your own right now, except you're here at the review, so I can talk about it, right? Okay, So let's talk about Miranda. And Miranda is actually, have you guys, anybody study psychology? Split personality disorder? Split personality? I don't know if it's real or not, but Miranda. Yeah, is that, I don't know if it's, I'm not a psychologist, so. Yeah, so, anyways, let's take a look at Miranda. Okay, Miranda's got some issues with its personality, okay? So you can see there's really some interesting, I don't know what to tell you. But anyways, we've actually taken spectroscopic data to analyze what it's made of. And Miranda has two parts to it. We actually think it's the merger of two bodies, right? Two bodies got together. So it's kind of a weird looking world, right? It's a moon. And the top half looks kind of normal, like, hey, like a moon. And then this is all warped and transfigured, right? It's been melted, and clearly there was some kind of energetic event there. So that's just curious, but it's probably the merger of two smaller bodies, right? Can you see it? So this is what you get when you take two smaller bodies and you mash them together. Miranda is an example of that, okay? So the early solar system was violent and energetic, okay. Okay, and then we've got retrograde orbit. This is a really weird thing. Retrograde orbit, did you form? Okay, so a satellite or a moon that is going the wrong direction around a planet. So if I look at the moon and all of the moons of our solar system, they go the same direction. That's not true. I just told you something false. There's actually some moons that go the wrong way, but most of them, our moon goes the same way, right? It means it formed very early on in the solar system from the original disk material. But a retrograde orbit is a sign that that object was captured, right? It's captured because it came later and was actually captured and started going in the wrong direction, okay? So it doesn't go the direction that the planet is rotating. It did not form with that planet. Okay? It could not have formed with that planet. So a retrograde orbit for a moon is an indication that it was captured. If we saw a planet doing that, by the way, that would mean the planet was captured by the sun as well, but there are none that are doing that. Okay, but there is a moon of Neptune called Triton, which has a retrograde orbit. It's the biggest moon that has one like that. But probably Jupiter and Saturn have lots of them that do that. They have captured many objects. And the reason it's also interesting is it has geysers as well. Okay, these are cryovolcanoes again, but this one is really strange. It's not water. It is liquid nitrogen geysers, right? This is pretty crazy. But again, it's further out, so it's much colder than the area and the environment of Saturn. And so liquid nitrogen geysers. Okay, so if you guys just hang out a couple more minutes, if you need to go, you need to go, but we're almost done. How does the sunlight change as you go further away from the sun? It gets dimmer. That's the answer. No, you need to know a little more, right? If you're talking about Earth, we'll call it 1, right? If you go twice as far, what happens to the intensity? 1/4 would be 25%, right? That's 25.25. Okay, what if you go 5 times as far? Jupiter's orbit, right? So 1/5 squared is 1/25. 4% of the light, right? 0.04. If you go to Saturn's orbit, which is 10 AUs, 10 times as far, what's the amount of light? 1/100th, 1%. Want me to do it again? What was it? How does the sunlight intensity change when compared to the Earth? Oh, the equation is, oh, let me write it down. Thank you. Slow it down there, Sean. Don't know what the heck you're talking about. Let's try it. Thank you. Actually, I really appreciate that. That'll make it, it'll make the review better. You'll actually go like, I understand that now. Okay. All right, so we're talking about the intensity of sunlight. The equation for the brightness of a star, it turns out, or the intensity of sunlight is B equals L, what's L stand for? The luminosity, the amount of light coming out per second out of the star, divided by 4 pi. Don't worry about that. That's just there. But here's the important part. D squared, the distance squared. Okay. Oh, shoot. Oh, it's still on. Never mind. Okay. I thought I switched off my mic. I'm not mic'd. How could I drop the mic at the end of the day? No, you didn't get that. Okay. All right. So the stars here. If we're here at Earth, right, then this is 1 AU, right? So we're going to call the brightness whatever. We'll just call it 1, whatever that is, right? Brightness 1. And now if you go twice as far, right, then this distance is going to be twice as big. But the only thing we really have to think about is 2 times the original distance. Everything else will stay the same, but this is now going to be twice as big, but that gets squared. And so that extra factor is the key to it all. Yeah, it's 2 squared. So everything else is going to be the same, except you're going to get a 1/4. And then it'll be the original. Let me put an E here for Earth, right? Earth. Okay, then you get everything is the same, except it's now 1/4 of that. Okay, is that too much math? But that's where it got. That's why we were talking about this distance squared. So if you go to Saturn, it's 10 times as far. So you get 1/100. If you go to Uranus, it's 20 times as far, 1/400. Neptune was 1/30 squared, 900. Okay, all right. Okay, how does the rings, okay, sorry. How is Io or Io the most volcanic body in the solar system? It's right next to what body? Jupiter, and it's getting so close in orbit, I think 18-hour orbital period. It's really close, right? So it's being stretched by tidal heating, and that is, it should have cooled off, but it's getting heated by Jupiter. And why is the ring structure so special? It's enormous. It's 80,000 miles wide, right? And then it's 10 meters thick. It's incredible. It's just like nothing else that I've ever seen. It's incredible. So the structure being so huge and yet so skinny in one dimension is really remarkable. That's not what nature does very often, right? It's pretty rare to see something like that. And yet it happened, so Saturn sees that. Okay, why are rings visible? We already talked about that. That would be the albedo, right? Saturn has icy crystals, which makes it very high albedo. And why is Titan so special? Okay, so a couple of things now. This is really key. Titan is special not only because it has an atmosphere, but we see the weathering taking place, and the pictures the Huygens probe showed us were smooth boulders, right? In the foreground of the picture. That was amazing. So on Titan, you have mountains, you have lakes, you have rivers, you have a process of rain and everything, you have erosion, all that stuff. But what are the mountains and therefore the rocks made of on Titan? Water ice, okay? The water only has a solid form on Titan. It never gets cool enough to melt. And that means the liquid is not water. What could it be? It's hydrocarbons, these organic, organic compounds. Okay, that was right. So methane, ethane, propane, butane, all of these anes, right? That in this cold world, they exist as liquids and gases, okay? And we see rivers and lakes, and we see, we've seen reflections off the lakes, right? Things like that. Why does Uranus have the most extreme seasons? Everybody remember the tilt of Uranus? It's 98 degrees, right? And therefore, when one side is facing the sun, only that side is getting illuminated by sunlight. This gets none, right? And so what happens is that it has extreme seasons because one side will get nothing at all, and the other side will get it. So we can see clouds on Uranus and Neptune that change according to the season. That's about the only indication that it has seasons, but it should have them. And Uranus takes how long? About 84 years to go around. And so 1/4 of its year is spent as summer, 1/4 is spring, fall, winter, spring, right? So about 21 years per season. That was one of the questions. Oh, am I going to do those? We're almost done? Okay. What's peculiarity of the ice giant magnetic field? They do not align with the rotation axis. We don't know exactly how, but somewhere maybe in the outer mantle, these are being generated by the dynamo effect, but not by a core dynamo effect. What is so unusual about Triton? It's going in the wrong direction around Neptune, right? It has a retrograde orbit. Where did it come from? Okay, so that's the clue. It was captured. Where did it come from? It's a Kuiper Belt object. This is really cool. So after this next exam, we're going to talk about Pluto. And you'll see it's got some of the same features. It's pretty exciting. Compare and contrast the layers inside the giant worlds. Okay, so the core is probably metal silicates, right? They've got an Earth-sized core, all of them. But the difference is Saturn and Jupiter have more mass, right? And therefore they have a metallic hydrogen layer, whereas the other ones do not. And then Uranus and Neptune have this mantle made of ices. Jupiter and Saturn do not, right? The outer layers do have lots of hydrogen, molecular hydrogen. Okay, all right. The 4 Galilean moons, we've talked about them before, Io, Europa, Callisto, Ganymede. And the rotation rates and relative sizes. Okay, how big is Jupiter compared to the Earth? 11 Earths. Saturn, 9. Uranus and Neptune, 4 each. Okay, rotation rates, Jupiter, 9.5. Saturn, 10.5. Uranus and Neptune, I forgot exactly. 15, 17 and 15? What's it?
17 and 16.
17 and 15. Okay, yeah, that's about right. Orbital periods, Jupiter takes 12 years to go once around. Saturn takes 29 years. Uranus takes 84. And Neptune, anybody? 165 years. Okay. So again, if I asked you a question about seasons, it would be 1/4 of that. Okay, orbital periods. Okay, that's it. All right, let's do the most missed questions from last time, the preview questions. Preview. Here we go. Preview questions. Okay. Those of you watching at home, we're doing the preview questions. Okay, here we go. All right. No picture, no taking pictures, but you can. Oh, shoot. It's on YouTube. Yo, I can put it on YouTube. It's on YouTube right now. Yeah.
Oh, sorry, I had a question from a while back. The sunset on Mars,
Why does what?
why is the sunset on Mars?
Oh, the sunset on Mars is blue because the sky is red. The particles are larger in the atmosphere of Mars. They scatter the long wavelength red color. So the sky is red. And then as the sun is setting, all of the long wavelengths go away, but the short wavelengths survive. And that's the blue and the violet color. Okay, so in the same way that on Earth, only the longest wavelengths survive because small particles in the atmosphere are scattering light. So it's because of the wavelength of light. Yeah.
I'm confused with caldera and corona.
Oh yeah, sure. Caldera and corona. So caldera is what happens after a plume of the mantle material comes up and swells the surface. You make, like I said in class, it's like a pimple. Do you remember that? And then it oozes, and then it oozes out. It's a volcanic thing, but it's not erupting. It's just oozing, and it makes this big pancake of material, which we call a corona. But after the plume recedes, falls back down, you're going to see there's a depression in the ground. It looks like a crater, but it's not a crater. It's just because the crust material is not being held up anymore, and that's called a caldera. Okay, so we find them on Earth inside of the top of volcanoes.
The last bullet question we found from the slide.
It was there or wasn't there?
Is it there in chapter 8 slides?
In chapter 5, what does yours say?
Well, are these found? Sorry. These can maybe found in the slides. That you show through class. The slides.
It can be showed in there. Yeah.
The PowerPoint?
Yeah.
Okay.
Yeah. But I just said them out loud. You didn't hear me? I'm too fast. Okay. Do you want me to tell you one more time?
Yes.
Yeah, why don't I tell you? What do you want? Rotational periods? Oh, no, the sizes. Start with size. So Jupiter. Let's start with which one?
It's both. It's rotational.
Yeah. Let's do one at a time, though. How about the size first? Okay. So Jupiter is about 11 times the size of the Earth. Saturn is 9 times the size of the Earth. Uranus and Neptune are 4 times the size of the Earth. Okay, then what? The rotational rates. Okay, so Jupiter, about 9.5 hours. And Saturn, about 10.5 hours. Uranus, about 17 hours. And Neptune, about 15 hours. So they're all faster than the Earth, but much larger, which means that the surface is actually moving much faster than the Earth's surface, right? And then the last one, the orbital periods. So Jupiter orbits the sun every 12 years. Saturn is 29 years. Uranus is 84 years. And Neptune is 165 years. Okay, so question number 1. We believe that all the terrestrial planets had primary atmospheres take care, of carbon dioxide. Only the Earth shows a secondary atmosphere of nitrogen and oxygen. What happened to most of the carbon dioxide that was once in the Earth's atmosphere? And the answer is life took it in and then died, and it settled down to the bottom of the oceans where it probably lived, and then eventually under pressure and time formed rocks, right? So it's still here. It is still here, but locked into the Earth's rocky material is the answer. Okay, typical meteors, little streaks in the sky, are the size of a grain, well, a grain of sand. A grain of sand. A grain of sand. Okay. The origin of Mars' moons, Phobos and Deimos, it has 2 moons, is they look a lot like asteroids, right? They're not round, they're small, and they look like asteroids. They could be captured asteroids, but there's something wrong with that hypothesis. What is it? The orbit is circular, and if it was captured, it should be highly elliptical. So that's a problem. It's really a problem. No one has been able to find a computational mechanism to do that, right? To become circular. There may be a way, but I don't know it, right? So at this moment, a better hypothesis is that it was ejected kind of like the moon was, and then formed this, just much smaller, much less material. But anyways, we don't know the answer. So it's currently an area of active research, okay? And so when will we find out? Probably the first time we take samples of those moons, right, is when we're gonna really find out. But even then, we don't know for sure, right? Okay. Number 4, can't update Chrome. Okay, ignore that. Don't worry, I don't know why. Uranus is tilted at an angle of 98 degrees to the vertical and has an orbital period of 84 Earth years. As measured in Earth years, how long would summer be? And I think we talked about this already. The answer is 1/4 of its orbit, right? So 21 years, 21 years, 21 years. Okay, good. So this is the questions that people got wrong the most. Over half of my last class got these questions wrong. So these are kind of factual, lots of factual questions, but the asteroid belt, where is the asteroid belt located? Between Mars and Jupiter, mostly more closer to Mars, less close to Jupiter. Is the debris field of a destroyed planet? Nope. Okay. In fact, all of them, actually, this is kind of an interesting little fact. You don't need to know this, but if you were to somehow lump all of that stuff together, you would get something smaller than our moon. Smaller than our moon, right? All of that. Anyways, it was kept from forming a planet by the gravitational disturbance of Jupiter, right? Probably that is the best answer, right? Nothing big formed there. Consists of roughly spherical bodies? No, none of them are spherical. They're too small. Well, okay, a couple of them are, but they're really big, right? The biggest asteroid is called Ceres. That's spherical. You don't have to know that. Contained as much mass as Saturn, not even close, right? Less than our moon, actually. Okay, the right answer was kept from forming a planet by the gravitational disturbance of Jupiter. Okay, Earth's magnetic field is created by, electric currents of some kind in the outer core of the Earth. Okay, which of Jupiter's Galilean moons contain liquid water? Liquid water, oceans. Liquid water. How did I do that? You know, that's one of those psychology tests. Like you didn't notice that, right? You could tell I wrote that. Okay, here we go. So Ganymede, Europa, Callisto, and the answer is all 3 of these. The only one that doesn't have water is Io or Io, right? That's the only one that doesn't have water. Everybody else does. And how do we know that? I didn't go over that in class, but auroras have been photographed for all of them. And so somehow this is not only water, but salty water. I don't know if that means anything, but it conducts electricity a little bit. Okay, there's a flow. Not exactly conducts, it's more like it is electricity itself. Okay, Triton is special because, unique because it is geologically active. That's true. It has volcanoes. They're called cryovolcanoes, but that's not unique. We have other moons. Enceladus, Europa are both cryovolcanoes. Io is regular volcanoes. That's geologically active. Has retrograde orbit. That's the one, right? It has a high albedo. It's not unique, right? Enceladus and Europa both have high albedo, okay? Has an atmosphere, okay. It does have a very tenuous atmosphere, but much less than Titan's, okay? So the only one that's really unique is the retrograde orbit. A body passing through the Earth's atmosphere that creates a streak of light is called, this is a super easy one, It is a meteor, okay? But it turns out over half of my class got that wrong, but you guys won't. I don't know why they got that wrong. But, you know, because the other words, you don't know the words maybe. Okay, but everybody clear? Going through the atmosphere is a meteor. And the last one, a meteor shower occurs when a comet breaks up? No. Okay, that actually would be amazing, but that's not it. Okay, the Earth passes through the debris left in a comet's orbit. C is the right answer. Okay, that's it. Well, we just went over a little bit. Thank you guys for being. Oh, you question? Yes. 9. A body is a meteor, right? So meteorite, it landed on the ground. Nova, we haven't learned about that. That's actually a kind of a flash of light. We're going to talk about it for the next test, but it's a star that's brightening temporarily. And meteoroid has not come into the atmosphere yet. The answer is meteor. Yeah. Oh, number 6, go back. Sure. Electric currents in the outer core. Yeah. All right. Yeah, if you didn't sign in, make sure you sign in. Thank you, everybody. Hopefully at home. Nobody said anything. Maybe, oh, I got a thumbs up. Thank you for the thumbs up. Woo! I got 5 people watching.